Okay, guys. Hi, Bob Cheesebro. We're talking about the essentials for Intel Extension for Scikit-Learn. This is the CPU focus. Just want to give you a sense of the learning objectives, just what we're aiming for essentially today, but also a peek into what we're going to be doing in a month. And so into this particular workshop, it's not really a webinar, it's a workshop today. You should be able to articulate the value of the AI kit. What do you get out of it? What's the motivation? What's in it for you, the developer? And then where to get it, how to describe the key components here that we're going to be focusing on today, the Intel Extension for Scikit-Learn. And then you're going to be able to apply accelerations using essentially a couple lines of code to accelerate supervised learning and unsupervised learning algorithms. And so that's what you're going to be able to do. You will be doing that today. And so just a little bit of a background, just kind of briefly, the One API is really an industry initiative, and it's a unified software development environment across CPU and accelerator architectures. And it's based on standards. And so some of you may have been taking some courses from some of my colleagues, Praveen and Rakshith and others, on standards such as SYCL, which is proposed by the Kronos group, cross-vendor compatibility to accelerate a wide range of accelerators such as CPUs, GPUs, FPGAs, AI accelerators, and so on and so on. What we're going to be focusing on today is really the Python interface to a lot of this stuff to let us do AI. And so that's kind of where we're headed now. And the AI, Intel makes several reference implementations of that industry standard. And so we have toolkits. And so one of the toolkits that we address is called the AI Analytics Toolkit. And the AI Analytics Toolkit, where we're going to kind of be focusing on today and drilling down specifically to one subcomponent within that toolkit. But there are other toolkits available. There's the OpenVINO one, there's one for IoT, for rendering, for HPC, and so forth. We're going to focus on the AI Analytics Toolkit, and within that, we're going to be focusing on Scikit-Learn. But the AI Analytics Toolkit really provides access to these lower level accelerators via a interface layer. The One API product has components that are all wrapped within that overarching umbrella of the AI kit. And so some of those lower level libraries are 1MKL for doing matrix manipulations and BLAS computations very quickly. The 1TBB, which is 13 building blocks, 1VPL for vision stuff, 1DPL, 1DAL, which is what the Intel Extension for Scikit-Learn really camps on, is the data analytics library, 1DAL, and then 1DNN, which is a toolkit for deep neural networks and accelerating those, and then 1CCL. So these are kind of the constituent families. And these things help to accelerate various ones of them. When onesies or twosies or one at a time, will accelerate the common suspects that we use in AI. TensorFlow. TensorFlow is accelerated by 1DNN. PyTorch is accelerated by 1DNN. I won't talk about Modin yet today. I'll talk about Scikit-Learn, which is accelerated by the 1DAL. NumPy is accelerated by 1MKL. And other things, because NumPy also, and all these others, are take advantage of the lower level C++ compiler, giving access to auto-vectorization and cache optimizations, memory hierarchy utilization, which really gives you much higher benefit when you call these, for example, NumPy libraries, and do the right things with it. And it'll be the same thing in Scikit-Learn. So you get acceleration not just from MKL, but also from C++, memory management, cache hierarchy use, and so forth. So these are some of the things that we're going to be looking at in the One API Analytics Toolkit. It's really umbrella around all of these. This reference kit that we have around all of these lower level frameworks or whatever. And so we have Intel optimization for TensorFlow. We have an Intel optimization for PyTorch. We have Intel Neural Compressor. This is on the deep learning side. Now, let me just say that we work very hard, Intel works very hard to upstream our optimizations to the stock version of TensorFlow. We work very hard to upstream our technologies, all of our instruction set architecture, all these libraries that let us get at that, we upstream that to PyTorch, the main stock version, and so forth. But this AI analytics toolkit, the cadence at which we can refresh this toolkit is typically faster than the rate at which they bring these kinds of technologies back into their own main lines for the stock versions of PyTorch or so forth. So typically the AI analytics toolkit may provide a little bit faster boost than what we would have in the stock version, just because of that cadence of the release cycles. So what the encouragement here is to do is to make sure that you're always updating, keeping up with your latest TensorFlows, PyTorches, Scikit-Learns, and so forth, and then update this package as well. Now that's just a general broad bath that I'm describing of all these things. Beneath the hood, and later in 2023, I hope to cover more about how you can get some phenomenal speedups using NumPy down below, SciPy, Pandas, and those things. My colleague here, Praveen, has told many of you about Numba, but today we're going to focus on Intel extension for Scikit-Learn. And so with that, let's dig a little bit deeper. And so one of the things that you may want to understand is where, if you're not on the Dev Cloud, for example, how can you get a hold of the AI Analytics Toolkit? Or how could you just get a hold of just that subset, just that Intel extension for Scikit-Learn specifically, if you didn't want the broad thing? I would recommend doing the broad thing. But there are a couple of ways to do it. Typically, you can do all the natural things. You can do conda installs, pip installs. You can get a Docker container, all those things below. And I gave the URL here, so you can go grab it if you want it. So it's all the standard things that you would do. Pip install the Scikit-Learn EX, for example. And so if you want to grab the comprehensive library, you go down here, down below. If you want to get just the Scikit-Learn extensions, it's this link in white. So you can do either. And so the motivation here is for you to be able to achieve acceleration on Intel current and future CPUs. Next month, we're going to be talking about the Intel current and future GPUs, and to be ready for future innovations from Intel. And these can be achieved with just a few lines of code. And you'll see that today, that with just a couple lines of code, we can really get some cool performance acceleration. Again, just a statement that today is on the CPU discussion, and then in a month, we'll be talking about the GPUs. So what's in it for the developer? What's in it for you? We're looking at accelerations effectively. So what you see here is just a high level pitch. Don't bother trying to read the words. You'll see it in the lab, actually. This is actually on the GitHub site where they actually did some competitive analysis to just see what overstock, what kind of accelerations were we getting at this point in time when these things were generated, when you use the Scikit-Learn extensions versus the stock version. Now, Scikit-Learn is different from a lot of the other frameworks that we're talking about, in that Scikit-Learn, the community basically wants to just, Intel, if you guys want to do it, just do your patching, do that extra library, the Intel extension for Scikit-Learn. We'll leave the stock the way it is, and then you can have this extension. So these are the kind of speedups you get. One for training, that's when you use, that's that background graph there. When you use the fit function, you're doing training, and so you're going to fit a model. And so these are the kinds of speedups you get for a wide variety of these algorithms. The common suspects, 30-ish some odd suspects from Scikit-Learn. We'll go over some of these suspects, what they are. The lower graph, the one in the foreground, is for inference. So this is when you do the predict or you do the transform. So these are the kind of speedups that you get. And different algorithms and different data sets with those algorithms will have different sensitivities to how fast you speed things up. It really depends on the size and shape and complexity of your data sets, the kinds of speedups you can get. But typically they are significant, let's say. Okay. So just quickly, I'm going to go over some of the gallery of the algorithms, because I don't want to just burden you with just talking. This is intended to be a lab. But on the left side, we have the unsupervised learning routines. dbScan and k-means are two of the algorithms that we accelerate, and you're going to feel the acceleration. You'll be able to see it. You'll be able to play with it for these unsupervised learning clustering type of algorithms, where you're not trying to have the data tell you anything that you are specifically looking for, like how does it match my labels. In unsupervised learning, you are trying to just say, how does the data just naturally group together in clusters? And so dbScan and k-means are accelerated, as well as nearest neighbor. Now, nearest neighbor, you don't think of nearest neighbor because you don't hear it this way as being an unsupervised learning algorithm, but you can use it that way. And its offspring is something we'll talk about in the third column here in a little bit. But you can use nearest neighbor, not k nearest neighbor, but just the nearest neighbor, to give it a set of features from let's say a tabular data set, and it will compute the nearest neighbors, find a matrix, basically a distance matrix for all those tabular entries. Principal component analysis is a really heavy hitting algorithm that's basically uses eigenvalues, eigenvectors under the hood. It does a little bit extra linear algebra on it to find those components within your data that explain the largest degree of variance is principal component 0, and the orthogonal to that is the next principal component that explains the next most amount of variance. And so it's used all over in AI. And so anyway, we've accelerated this one. We've accelerated t-SNE, which is really used to compress. Both principal components in t-SNE are used to reduce dimensions. But t-SNE is used for, it's a non-linear algorithm that allows you to compress for visualization purposes many non-linear manifolds down to 2 or 3 dimensions that you can actually visualize. Linear regression and its variance. Elastic net, which is kind of a combination of lasso and ridge regression. Logistic regression, which is really more of a classifier. We accelerate all these things. K-nearest neighbor. So we mentioned nearest neighbor. K-nearest neighbor is actually a classifier, and K-nearest neighbor is accelerated handily with the Intel extension for Scikit-Learn, as is random forest. In random forest, some people don't know, but there's both a classifier and a regressor that you can use. We accelerate both of those. Support vector classifier, another very popular routine to do both classification and regression, and we have accelerations for those. K-nearest neighbor regressor, and then these kind of utility functions, asserting that all your data is finite, or computing the receiver operator characteristics area under the curve score, for example. These are the things we accelerate. Train test split. So these are functions that you probably use a lot, right? And so you have faster versions of them. Pairwise distance, and we'll see kind of a cool application of using pairwise distance, and we accelerate it. And so to use these, we have to do something called patching. And so just to introduce this idea of patching, what we do is you will import the Scikit-Learn EX after you've installed it, or on the dev cloud, it's already installed. In your code, in your Jupyter Notebook or in your Python code, you would import Scikit-Learn EX. Okay, and typically you'll see the variance of it. We'll do from the Scikit-Learn EX and import a certain library and so forth. But what the goal is we're going to import this library, and this library has the fastest versions, or the very fast versions of these algorithms. And so you can control its behavior by using some command line flags. There's actually a way you can use an environment variable, so you can specify that any notebook or Python routine that I run could have patching turned on by default, and it will run the fast Intel versions. Or you can do it on a command line. You're going to actually do this in the lab. You're going to take a Python, you're going to take a Jupyter Notebook, convert it to a Python file, and then you're going to apply the special command I'll show you to apply the patch at a command line. Or you can do it within cells. You have surgical control. We have all kinds of ways that we can control patching. In its simplest incantation, patching is done in the following way. From the command line for a Python file, you would simply say python-m scikit-learn ex, and then you give it the name of your application. It'll patch every algorithm in there to use the Intel extensions if they are available. If we've done an optimization, it will choose that one. Inside a Jupyter Notebook, or actually within your Python code itself, you could do these lines too. You could say from scikit-learn ex import patch sklearn. And what this does, when we invoke that function, patch sklearn, we are setting up a listener. And that listener says, okay, I'm ready. Anytime from now on, throughout the rest of my execution, I'm a thread now, a thread of execution. If anybody imports anything from the Scikit-Learn library, I will go ahead and use the Intel version if one is available. Otherwise, I'll use stock. Okay, that's kind of the idea of the listener. Now, you can also do the same thing to unpatch. So this gives you some degree of control. You can actually patch up to a certain point and then unpatch to a certain point and then patch again. So you can control the degree of patching, and you can actually control the degree of patching at a more surgical level. You can say, look, I only want to patch, or I only want to unpatch SVC, or train test split, or PCA, or a combination in a list of these things. And so you have a very coarse grain that you can just turn on. It's almost like the lights to your house. Like you can turn on the power to your entire house. And then from then on, now you can go into each room and turn on lights on and off, or you could go to a lamp and turn it on and off, and you have finer and finer and finer down to an LED in your hand, and you're pointing it, you're waving it around. You have finer and finer degrees of control over what you light up. And at the end of the day, if you wanted to unpatch everything, you could do that. If you wanted to just turn everything on, you could do that. And so this is the idea. So the idea here is that if you use patching correctly, let's say that somehow you find a pathologically misbehaving algorithm with the patch Scikit-Learn. And I've only seen this happen. I've been playing with this a lot. I've only seen it happen on one small data set that I had when I was trying to use train test split. And my performance is just slightly slower with the patch version than it was with the unpatched version. Well, no big deal, because I can guarantee I get my latest and greatest performance because I just say, well, then unpatch that one, okay? And I patch everything else, and I get the best performance no matter what I do, because I can look at it and measure it, and I can say, okay, unpatch the slow stuff and keep the fast stuff. Generally, you don't have to do that, but it's available when you need it. So this is just a way to get all the names of the functions, the decoder ring, so you know how to surgically unpatch something. You can say, well, just this one name. So this is where you get the names. And then this is how you do patching. So patching is real simple. Patching is these two lines of code. You, from Scikit-Learn EX, you import the patch, that listener, patch Scikit-Learn, and then you call it. And you do that before you import the rest of your stuff for Scikit-Learn. Okay, and that's it. If you just keep those rules in mind, you import these two lines and do that before you do the imports. Okay, you're good to go. Now, so what that then looks like, well, do I have to do anything with my code? Do I have to change the rest of the way I use that function? No, you use it just the way you normally would. So in the rest of your code, the train test split, for example, doesn't change one lick from what it was before you did any kind of patching. You can take your raw code, and you'll see this. I've got some practicums that you can use that are unpatched code. It's just as if you got it off of GitHub or whatever, and off of some forum or whatever you want to do, and then you can go in and see if you can patch it. And so this is exactly how we do it. And you don't change any of the lines of code other than inserting these two lines of code for the patch in the right spot. So that's pretty much in a nutshell what patching is all about. This is just a snippet of what you're going to see here in the lab, and this is almost our call to action to get ready to do the lab now. This is an example, happens to come from the support vector classifier. This is the results I'm getting on the CPU for this lab on the dev cloud. And so what we're going to do is pair an algorithm, in this case SVC, and I can control the parameters of it. I'm putting this in kind of like a dictionary, okay? And I'm going to pair the algorithm and the data, so I can generate synthetic data to try with that particular algorithm. And I can say the number of samples, that's how many rows, the number of features is how many columns, number of classes that we're trying to predict. So, that's, kind of your number of labels, or yeah, and then your number of informative could be, how many are really going to correlate and somehow give some meaningful information to your classifier. So you can control the kinds of things you want to do in the test, see what kind of speedups you get on synthetic data before you go hatching it in your production stuff. You get a sense of get some intuition, okay, for how it works. And then this is just a simple little, few lines of code that says in the real world, you would just patch it, and then you just call it as usual. And, you get your results, and we can plot the times. And this is the speedups that we're getting. In this case, for this particular data set, synthesized data set, we were getting like 12x roughly speed up on the dev cloud. So with that, we're not going to do the survey yet. This is just my segue into the lab. So we'll come back to this slide that I would like to have you guys be thinking about filling out the survey, because we would like to improve the course as we go on. With any luck, I'm going to be able to switch over. Can you guys see my Jupyter notebook now at any point? Or are you
Yes,
still
Bob.
seeing my slides? Okay,
Yeah.
so you can see my Jupyter. So what we are going to do is I'm going to walk you through the dev cloud. So the first thing that you want to do is to make sure that you go to the devcloud.intel.com, one API, get_started. And so Praveen, if you can pop that link in the Zoom.
Yeah, I put it in the chat window.
Okay, so just go to this location and you enroll in the dev cloud if you haven't already. If you have enrolled, go ahead and sign in with your credentials. Once you've signed in, you go to this get started page, the devcloud.intel.com, one API, get_started. Scroll to the bottom of that page and you will see an icon at the lower left of the entire page called Connect with Jupyter Lab, and you can just launch the Jupyter Lab. There's a hyperlink there. And when you do that, it's going to bring you to a splash screen, something like this. This is the welcome page for the Dev Cloud. And if you click on the launcher is this blue button over here. It's a blue button with a white plus sign. And you can just click that and you will get another page that shows the launcher. The launcher has a number of kernels that we could launch. If we wanted to just jump into creating our own notebook, we could do that. Or consoles, we could do that. I want you to just click on our terminal down here. So you're going to click on the terminal icon, and that's going to launch another instance of the terminal right here. And I think, Praveen, you also gave a link to the, I can't see my screen because the controls for the Zoom are in the way. Let me see if I can move that somehow. Bear with me while I try to move my Zoom, or I'll have to move my browser, I guess. So let me move my browser around, and let's see if it'll let me do that. Let's just see if I can. That's just moving the one browser. That's not what I want to do. Let's see, Alt Tab. Let's go to get started. Let's go to the, oh, why is that thing in the way? Can I move this out of the way? Okay, I can move my bar out of the way. Good. So let me go back and find my, this is the developer cloud. This is, bear with me while I get my correct things going here. This is the dev cloud, and we should have the link. Praveen, do you have the link there for the, let's just do the GitHub. We're going to go to the GitHub link, and I will share it with you on the screen, and I think Praveen will be able to
Bob,
share that with you.
I put it in the chat window. You can take it from there.
Great. Okay, great. So let me just log on here and get it. So it's machine learning using one API. So the link Praveen shared in your chat, we're going to go to this GitHub link, and there's a README of instructions for you to follow. So there's just some preparation to run on the Intel Dev Cloud. You're just going to follow these instructions. Okay, so let's go do that, and you'll just follow me. So at this point, I'm going to make a directory called ML one API as per the instructions. I'm going to CD into that folder. And I don't know if you can see my font. Praveen, do you know if there's a way to increase the font size? I'll just zoom up like this. Maybe that's the best way to do it. So there's the, I'm CDing into that, and now I'm just going to do a git clone. Well, actually, let's follow the instructions verbatim. I think I did another step, and that is right here. We'll source this particular environment. So we're going to force a specific version of the library for right now. And that will just prepare our environment, get all the proper kernels set up for us and so forth. And once we do that, then we can activate base. Okay, so we'll go ahead and activate the base. And now we'll do the git clone step. So that same git that you're using to do the README, we're just going to do a git clone, and we'll specify the git clone from that location. And this will take a minute or two to git clone the notebooks and the data and so forth that we're going to download. Won't take too long. So just, Praveen, if we can just ping, I'll just ask, is everybody following along on this? Anybody having any issues getting onto the dev cloud, being able to follow along with the GitHub instructions, doing the git clone? If you have any issues, just raise your hand and let me know, and Praveen and I can help.
Please put it in the chat window and we can help you out if you see any issues. I don't see any questions in the chat window yet, but please feel free to put in the questions in the chat window, and we can help you out with you.
Yep. Now there's a number of things. So while I am going to be showing you some patching stuff, I'm going to bet that there's a couple things I'm going to show you just with respect to ML and using pairwise distance, for example, maybe you haven't considered before. And so stay tuned, because I think there may be some juicy things for you to see even outside of the patching. So we've gone ahead and cloned this. So now I have ML using one API. So I'm going to go over here what's called the navigation bar. The navigation bar is controlled by this folder looking icon. I can either hide it or bring it back. And there's a new folder called ML1 API, and that's where we just cloned this machine learning repository from Git. And we're going to start at unit number 1. It's called Intel Extension for Scikit-Learn. So we're going to drill into the 01 Intel Extension for Scikit-Learn patching CPU folder. And there are 3 notebooks. Let's start with notebook 1.1. And I think if I remember correctly, I think I left some little speed bumps in here for you to be able to apply the patch. So it just says insert code here, and hopefully I didn't give the solutions away, but I'm just going to go ahead and run this cell, and then we'll go in and we'll apply the patching. And so what we're doing here is that we are using patching to control a classifier. Okay, so we are going to apply patching to a classification routine, and this is on the cov type data set. So this is a coverage type data set, basically from the US Forest Service, that looks at different kinds of tabular measurements about soils and pHs of soils and different conditions like that. Several, multiple columns of that kind of data. And to be able to predict the foliage cover, whether it be scrub oak or a certain kind of pine or juniper or whatever you have, the kind of coverage that you would get as predicted by that tabular data set. So what we're going to do here is I'm just scrolling down to, let me just minimize that.
Bob, can I interrupt you for a second? So just, someone is seeing issue with the Jupyter lab taking some time, but just, we'll just get a little bit slow down here and give some time to participants. So if you are seeing that, the notebook taking forever, if it's a new account, it is expected that it may take a couple of minutes, or try launching the Jupyter lab again. So, but give it a little bit of time if it's a new account. If it's an old account, you may try relaunching and, refreshing the browser.
Yeah, and another thing that sometimes helps, and one of the things I'm doing right now is I'm using an incognito version of the browser, so that all that cache history and whatever is cleared out, and sometimes that helps too. But
thanks for the point, Bob. Yep.
Well, just let us know, and our next stop on this bus is we are going to apply the patch. We're going to import the libraries. I'm going to go ahead and in just one line of code import both the patch and the unpatch so that the libraries are ready to go for me. But then we're just going to apply this patch. And I've conveniently told you where I want you to put it, insert the patch here. So I've just done a Control-C, Control-V and put it in here. But for those of, while everybody's kind of catching up and kind of doing their stuff, let me explain again just what's going on here. When I execute this patch command, patch Scikit-Learn command, I'm setting up a listener that is then going to listen for any future imports from Scikit-Learn, any of the imports at all, and then we'll compare against the ones that it knows that it's accelerated in its list. And if it's accelerated one of these, it will use the accelerated Intel version of it, and that can be significantly faster. And so that's what's going to happen here. When we turn on this listener and then we apply this patch, we're going to get the fast version of this code. And so if I were to run this cell, down to this cell, we would get the patched versions of this. So I'm just going to go ahead and do that. I don't want to get too far ahead of everybody. If you're still struggling with getting things going on the I did this earlier today, but this is a new instance. So one key step that I did not do myself that's in your Git steps is to make sure you do this pip install of the requirements file. And I had not done that. So let me go back to the terminal, and I'm going to cd into machine learning. And you'll see that there's a requirements.txt file in here. And if I just do a pip install -r requirements, it will go ahead and install the Seaborn and the various packages that we're going to use. And that was all part of that same Git instruction from that Git README. I just neglected to do that for you. So let me relaunch this notebook, and we'll just try it again, see if we have better success. So here's the notebook. Yeah.
Hey, Bob, can you just walk through the launch Jupyter Lab page again?
Yes.
One of the participants is asking that. So
yes.
If you can show the way
yes.
how, go to the get started page and yeah.
Yep. So what we'll do is we'll just go to devcloud.intel.com/oneAPI/get started. And I don't know if you can see my screen very well. I'm trying to do the thumb wheel to scroll. It's not getting any larger.
Yeah.
But Praveen has put that in the chat window. So that's the link. You just go there. And after you sign in, you'll know you're signed in because it will say, what would you like to do? You sign out, and you'll see your user name or number over here to the right. So this says that you are signed in. So if you've enrolled, if you haven't signed in, if you haven't enrolled, you'll see two buttons over here. You'll see sign in and enroll. If you haven't enrolled, enroll. If you have enrolled, sign in. Once you've signed in, you will be at this step where I am, and you can just scroll to the very bottom of the page, and there's a connect with Jupyter Lab icon and this little paragraph here. All you want to do is launch this Jupyter Lab. Just click on that hyperlink, launch Jupyter Lab. And what that will do is that will bring you up to effectively this welcome page on the launcher. You'll get something that looks a lot like this. So we'll wait just a little bit for that to happen. And we've got plenty of time. We've got, a total of 2 hours to play here, and we're only into it for about 35 minutes. So don't stress about it. The other thing is that this GitHub is not going away. It's there for the count. The dev cloud is not going away. It's there for the count. We're recording this lab session, so it will be there upon the termination of this presentation. So don't stress. I'm going to try to be patient, let everybody catch up, and we'll try to all go together. But if you're just having some technical issue and it just doesn't seem to be resolving, don't worry about it, because everything that we're doing here, you can follow along at your own pace later on, and you can go as quickly or as slowly as you'd like to go. And so I just wanted to offer that as a kind of a comfort blanket that, we have plenty of resources here. DevCloud's always going to be there. The GitHub's there. The video is here. We can provide the slides, so all of this will be there. So just relax, take a breather, and it's going to be okay. And then please ask Praveen any questions in the chat. If you kind of let Praveen know, once you get onto this step, let us know that, yes, I've successfully launched Jupyter. That would be a good thing to know. And then if you've successfully cloned the repository, let us know. And that'll help us gauge, when we can move forward together. So Praveen, I'm going to kind of lean on you for when I can kind of move forward.
Yeah, let's go. I think.
Okay. So let's see. Now somewhere here I did my patch. Let's just run this code because I've done the no module Seaborn. Let's see here. Let's just discard that. We should be in machine learning using one. So let's just do the pip install. The requirement should be met. Okay, that's there. Let's go to the launcher. We'll go to, let's just make sure that we're in the right step here. Machine learning one API. Yes, we're there. One, okay, we'll do the patch. And then we will run this. We'll do the run all. Oh, it may be, I know what it may be, is the kernel that's being used is right here. 2022, that should be fine, but we'll just see if it gives me an error. It's having trouble with Seaborn. Which one are we logged into right now? We are in, okay. Let me just see if it allows me to try, 2022.3. If you have the error that I'm seeing, it's because we are where it couldn't do the Seaborn. It's because I asked you to launch the 2022.2 library. This is the environment variable that we're doing. So in my Git instructions, right in this step, right here, we had sourced the environment variables for 2022.2, but the Jupyter Lab is only giving us 2022.3. So I'm going to force this environment. I'll have to change that GitHub instruction. We'll make it 2022.3, and we'll see if this corrects it. So now I'm going to have to do the pip install again, because this is going to pip user package install packages, please use. Okay. Yeah, this is why I went back to that other one. Okay. So Praveen, what the issue is that if I launch the 2022.3, there is an issue with it not knowing where the some of the files are. There's an issue in that set environment variables. And that's one of the reasons that I went to 2022.2. So now what I'm going to have to do is, because not everyone is going to be able to see 2022.2 from their Jupyter terminal like this. They're only seeing 3. And so we will probably have to inform the kernel
I think you'll
about
have to
that.
Create a new kernel for 22.2, and because Jupyter Lab directly takes from the environment variables, but not your terminal. It doesn't. So you'll have to create a new environment. Sorry, the 22.2 kernel.
Yeah. So hold on with me while I'm going to look up some stuff. So just bear with me. I'm going to find some instructions for telling the Jupyter interface where that 2022.2 lives. So bear with me, and let me just go here, and we will let me think here. We are looking for Jupyter. It's this command right here. And I am going to go back. I'm going to call this display the name to be 2022.2. .2. Oh, I need to do that for base, actually. And we will do that same thing on 2022.2. And now if I come over here, I should see a 20, maybe I have to relaunch the notebook. I'll walk you guys through these steps, but I'm just going to see why it's misbehaved. Okay, and now we'll see if it knows about the Seaborn. Is it going yet? Let's see. I'm just looking to see how well this workaround is working for us. So bear with me, and then I'll walk you guys through the steps.
Bob, can you also look at the chat window? I see one of the participants posted that the GitHub instructions worked for that particular participant, and he was able to run the notebooks with 22.3 kernel. So
okay, let's just look at the meeting controls. Let's see, go to the chat. Chat. I've launched Jupyter. The GitHub instructions worked. Okay, so I'm glad that it worked for you. Some people were able to run it from 22.3. That's great. Mine did not. Some people were able to do it as the instructions I gave you using the 2022.2, and that's great. I just created this brand new account. I had some issues with DevCloud about 30 minutes before our interaction together. And so something's amiss on mine, and I don't know why. If you're having the same issue as me, then the workaround that I did apply was to do the following. I needed to source the 2022.2 if you have the same issue that I had. And once I sourced the 2022.2, then I issued the following command, and I'll put this in the chat. So let me just see where my chat window went here. Okay, let's just, let's see. Let me see why I cannot see the, see hide thumbnails. Show active speaker. let's see if I can see my controls here for, okay, there you go. There's the chat. Okay, so I'm going to give everybody the chat. This is potential workaround to Seaborn not importing. Need to run pip install -r requirements.txt from 2022.2 environment to display 2022.2 environment in Jupyter. Do the following. And so this is the command to get you guys where you can actually do Seaborn. Some of you didn't have the issue, so we're good to go there. So so if you run this code, what you will see is that we did the patch, and all I'm trying to do, we're going to be comparing a patched version versus the unpatched version. Okay, and so we're going to be doing the patch version first, and then I'm going to do the unpatched version, and we'll just compare the two. We'll run them, and we will see what the speed ups are. Okay, and so by the time we get done with this little lab, you're going to know how to do those first two instructions to import the library and then to do the patch. And you'll be able to do both a patch and an unpatch. And the goal now will be able to see what the acceleration was, one over the other. So I'm rerunning all those cells, but so we've just run the patched version, apparently took about a second, and now we're going to run the unpatched version, and this will take probably 10, 11, 12 seconds, something like that, maybe 13. And so when that returns, it'll go ahead and plot it.
Bob, there is a good catch in the chat again. Looks like there is a small typo where for the unpatched time you were still trying to put in the timing for patch, so I think we'll have to change it on patch time.
Okay.
That's what I looked at the chat.
Oh, right here, probably unpatched time.
Right yeah, here. Right there.
Unpatched time is this. Oh, and then I'd need to say unpatched right here. Is that the,
yep.
Yep.
Yeah, okay. It's just printing the previous time, but it's still taking a lot longer and the graph's still right.
Okay.
Yep. Thank you for that.
Great, thank you. So what kind of speed up did you see? Were you seeing like the 12x or so? I'm running it now, but since I reran it after I made that change, it's going to take another 10 or 12 seconds or so to get us here. Thanks for that catch. But hopefully you're feeling in the hamstrings as you sit here waiting for this thing. When we did the patch version, it took about a second. And now as you feel the tension in your hamstrings as we sit here and wait, you're feeling not just seeing it on a graph, but you're feeling the temporal sense of time pass you by as we wait for the stock version to do its thing. So this took 72 seconds, okay? So this speed up was on the order of 72x, 63x, something like that, 63x. So hopefully you'll see that it's not just a graph, but you felt the burn, you felt the pain of this thing taking the time, right? And so that's kind of the goal of this exercise. So I'm going to go ahead and save this one. I'll put that into the GitHub here in a bit. But the next one is to spend more time with this motivation. And what we're looking at here is the unit 102. And this is just that description of these, where we are, in the Scikit-Learn and so forth. And this is just looking at the training, that is the fit function for all these routines, dbScan, k-means, knn, linear regression, logistic regression, and so forth, as it has been applied to a synthetic data set of 500,000 rows and 10 columns, 500,000 rows and 3 columns, 500,000 rows and 50 columns. And you're just seeing the effect of the same algorithm applied to different types of data. And it depends on the number of clusters, it depends on the number of columns and rows, all that stuff. But you're seeing that the fit function really can give you some significant speed ups here across the board, across a lot of these, support vector classifier and so forth. You're getting a lot of speed. And that's just for the train function. There's a similar one here for the inference function. Now, you may notice that there are certain algorithms where the PCA really got a good speed up on the training side, but then it's got a moderate speed up from the inference. And that's just where the computational load happens to be in PCA. And so you'll see, your mileage may vary, but the same kind of thing with KNNs. KNNs typically, I think it's the KNN that will train. It takes longer for it to, it's shorter for it, I think, to train, if I remember right. And where you really get the speed up is on the inference side. And that's because to train a KNN is hardly anything. You're adding another data point. It doesn't take much. So there's a little bit of acceleration that we do. There's some ancillary things that can go on because you're using C and C++ cache optimization stuff. But where you're going to really get the speed up is during the fit function of the KNN, because that's where the heavy computational load takes place. So different algorithms have different sensitivities based on where their computation really lies and the kinds of data sets that you feed it. So this is the point of this is that I gave you a test harness here, and I'm going to explain what this test harness does to let you test your own algorithms with data similar to the kinds of data that you have. Okay, so as a side journey, I went ahead and took a lot of the advice that we have from the website on the Scikit-Learn, which algorithms are accelerated for the CPU. I encoded it here in a spreadsheet or in a CSV file, and then you can print this, and so you can get different advice. What is this algorithm used for? What are the advantages? What are the disadvantages? What is the acronym? What is that secret decoder ring that if you want to turn it on or off with patching, what name do you use, right? And so all this stuff is kind of here for you to play with if you want. This is how you can query it. So if you wanted to find out more about dbScan, you can just do this defined function that I did to print the gallery of details for dbScan, and you can ask it, what are the advantages? What are the disadvantages? What is this algorithm used for? So this is just kind of a freebie for you guys. It's, if you already know that stuff, don't worry about it, but it does give you a little bit of an idea. This is where you can get those patch names that I was telling you about. And then this is just talking a little bit about the strategies. And we're going to go into this in the next unit, number 3, where we're going to patch using the command line. And then we're going to use these patching strategies that I've begun to show you already how easy it is. But so you can patch, you can unpatch. This is all the stuff I covered in the slides. This comparison function that I'm going to talk about now is really just a wrapper around the following idea. What we're going to do is we're going to go through a series of items in a dictionary, and that dictionary binds both an algorithm and a data set together so we can test them out. And so what we're going to do in this function is that we're going to recurse through that dictionary. We're going to figure out what the algorithm is, what the estimator is, what the data is, what the data generator is, and then we're going to set some timing. We're going to start timing things, okay? So that's all that comparison function does. The comparison itself, this get cases function, is really just going to return a dictionary. And this dictionary, I'll just kind of delineate here for you briefly. Again, it binds data with an algorithm right here. And so we can control the parameters that you pass to that algorithm. So you can give it the RBF kernel instead of the linear kernel, or what have you, whatever you wish to do with Scikit-Learn. And then you can specify the number of rows and columns and all the stuff for your data in a synthetic compilation. So that was the first entry of that dictionary. Here's the second entry. This one is also going to use SVC, but it's going to use the radial basis function kernel instead. So we'll compare timings, and then we'll give it a different set of data. Logistic regression. So we'll have a test against logistic regression with its own set of data. Remember, logistic regression is a classifier, so we're making a classification blob of data here. Okay, KNN classifier, another classifier, but we will generate classification type data. Now there are regression things that we can do, so we can test out the KNN regressor with its data, and notice that I'm making a regression type of a data set here with these kinds of parameters. Same thing, linear regression, ridge regression, principal components, and so forth. So now what we do is we want to feel the burn. And so what your job is to copy these lines of code right here. Oops, let's copy the lines of code from right here, and we'll insert them here. Yes,
can I
go ahead.
Sorry, I just got lost, but I'm back again. I lost all the chat, but there was a question, someone asking the small typo you fixed, right, in the previous code. We can please show that again.
Yes, I will show you that. Let me run all cells above while we're doing this. So that line of code that I changed, there was a typo, and I will fix that in Git. But that typo occurs in this cell. This cell is the exercise apply unpatch. So go to the cell that correlates to exercise apply unpatch. And at the very, very, very end, I was printing out the time. It's this line of code right here. It printed the time. It was printing about 1 second because inadvertently I told it to print the patched time. It looked like this rather than the unpatched time. So that's the only change. It's to that cell. Okay. And how are we doing on time? Yep. Okay.
All my chat history was gone, so you may just look into the chat window before there are any further questions. Thanks. Thank you.
Let's just see if I can find the chat function here. Okay, so there's 12. Okay. Okay. Let's see. The typo doesn't really directly affect the part where the ratio is calculated, right? It's just the printed value, exactly. So yeah, and if you didn't get a ratio, something on the order, if you did get a ratio, something on the order of one, you either patched both things, or you unpatched both things, or you didn't. In other words, you have to patch one of those cells and unpatch the other cell, and then you should get a ratio different than one. So let's just see. Did you apply? Okay, the typo. Yes. So hopefully, yeah. So now somebody's getting about 60x. Yeah. So it's working well for them. They're getting about a 60x speed up. So not bad. And you know it's true because you felt it in your hamstrings, right? It's not just a pretty graph, right? So yeah. So that worked. And so now what we're going to do, get cases is not defined. Get cases is not defined. Why is that the case? Get cases is defined right here. Let's run all cells and see what's going on. Get cases ran, and so now it's running the unpatched version, and this is going to take a little bit of time because it's running through a whole smorgasbord of tests, principal components, KNN, with various data sizes. So this could take a minute or two to run. And when it does that, so again, this is the feel the burn exercise. The intent of it is that I want you to not just see a pretty graph and see something in a slide that says something is faster. I want you to feel that temporal disparity, right? I want you to feel it as you're sitting in your chair, how uncomfortable it is to wait for the stock version of something when with a couple lines of code, you could get it to run fast, okay? So that's, in some ways I want to apologize that it takes so long. In some ways I don't. That's intentional. I want you to feel the pain so that it's not just seeing it in that graph, right? Like there's something about having to sit here and wait for 1 or 2 or 3 minutes for something to return. And so this is going to apply to all the codes that you're running too, right? I mean, it's amazing how You may be living with something and you don't know that it could have been a whole lot faster. And part of the reason I'm printing out those F1 scores and so forth also is that you can say, well, what am I giving up? Like, am I giving up any accuracy? Did I give up something on the precision or the recall or the F1 score? You might see a little tiny, decimal change somewhere. I have not yet, okay? Not to say that you don't, because order of operations, as you know, can have an effect. And anytime you do an optimization and you're dealing with floating point numbers, there can be, and sometimes you could almost say is bound to be, some degree of difference. But practically, to the degree of precision that we printed these things, there's no difference in the accuracy. Okay, so that's part of this goal too, is to say, what did you give up by speeding this thing up? So we'll just continue to let this thing bake. So this is the Unit 2 version, and then we'll do the patched version. So when you do the patched version, I gave you all the hints here to say, okay, this is exactly what I want you to insert. So I'm holding your hand for right now, but we're going to get to some practicums very soon where you won't have the hand holding. So it will be important that you get this idea of what's that pattern? What is it that you're doing? And really, all patching, whether you're doing supervised learning, unsupervised learning, doing regression, doing classification, principal component transformations, Disney, whatever it is, doesn't matter. The patching construct remains the same. You import the patch, you patch, then you import the rest of Scikit-Learn. That's it. You can control it. There's nuances I've showed you to be able to control that patching behavior. You can patch a specific thing using quotes and say patch just this, or you can put 2 or 3 things in a list in quotes and then patch those things, or you can unpatch those things. You can patch the entire algorithm. So there's wrinkles that you can apply to it, but I think you'll find that as a general rule, and this is something you should play with in these practicums, see what happens when you just do the global patch, and do you speed up versus not patching it? And then you can go in and more surgically patch things, right? And all the way down to whatever degree that you're comfortable with, but you will become very familiar with this pattern. And that's part of what I want you to do, is to just see that irrespective of the algorithm that you're going to patch, you don't change the algorithm one whit. All you do is you apply the patch before you do the import. That's the simplest explanation, okay? And then these wrinkles can come in, and you will see it here in version 2, in 1.02, because I'm going to ask you some questions that relate to the lexical reading of code. That is, like reading it as if you're reading it on a page, on a piece of paper. You've printed out this code on a piece of paper and you're reading it from top to bottom. That's the lexical approach to looking at this versus the dynamic approach. In other words, what does the thread actually see? And so knowing where to patch by looking at the code is going to become important. And so I'm going to throw you a little bit of a curve here. And so I'll walk you through that at the right time. I'm just running it right now to kind of show you what goes on.
Hey, Bob, so there's a question. When I look with top and view threads, I see a lot of Python threads running. Is that one of the features of the toolkit? I'm asking for more clarification, but if you got any
that you see a bunch of threads. A lot of scikit-learn algorithms will turn on n jobs or num jobs to -1. That's like their default, and that means use as many threads as you can. So we're not explicitly using it, and the NumPy library is not, I mean, the scikit-learn library that we're playing with right now is really targeting vectorization under the hood, but the scikit-learn library itself sometimes has that num jobs or job libs or whatever it is set to -1, which says use threads if possible. So they may have additionally in the scikit-learn algorithm used threading. And so you may see that in the tops function. You may see that more threads are being used. But what I'm articulating here, and it's kind of good news for us here in the AI community, or just developers in general, is what I'm describing here are the vectorization things that basically the one-DAL library is doing. That gets applied per core. Okay, so these speedups that I'm articulating here are per core because it's targeting the instruction set architecture that is made available in each core if it's a performance core. And so The fact that you get multiple threading, that's just a multiplicative benefit, right? If you get a certain performance advantage per core, and then you multiply that by X number of threads, well, then you get the thread performance times the vectorization performance, roughly. I mean, if you don't have race conditions and so forth. So that's kind of the idea. So yeah, you may see that on tops, but it's really, that's going to be a function of job libs, and you could actually specify, and we'll have to look up exactly what that parameter is. It's either in jobs or job libs. I forget what the name of the parameter is. You can look it up in Scikit-Learn. But you could set that value. By default, many of them are set to -1. If you set it to 1, for example, then it should restrict it to 1 thread. And we're still computing this this exercise. We did the one version here. I think this is the patch version, and we're getting some results back. And now we're feeling the burn of doing this in huge sort of test harness, unpatched. Did I should have said, okay, I said patch there, and I said unpatched there. Sorry, backwards. I did unpatched first, and now we're going to be doing the patched version. Still taking a bit of time, and then we'll just plot these results.
So Bob, the follow-up is, so we are seeing speedups due to the better use of AVX 512, for example.
Yes, that's exactly right. Yep. And what this does is this sets you up for not just your performance now. You're getting a certain performance now on the dev cloud. And yes, we've got a certain, these are just the login nodes. Okay. So they happen to have some AVX 512. They're not the super duper performance nodes. And so if we were to Q sub this against a higher performant node that maybe has, other, AVX 512 instructions that are built in that maybe the login doesn't have, then you would get more performance. And so the good thing here is that you're putting that onus, that burden of the performance acceleration on the library writers themselves. And so as long as you keep your libraries up to date, and then you move this code from, let's say that we were on an AVX 512 machine today, right, running this thing, you would get a certain speed up and it would feel good over stock. Okay, that would be great. But you'd be on yesterday's technology. And then you move to today's technology. You just move the code over and you don't change anything, and you get that performance benefit. And you didn't really lose very much in terms of code readability. You added a couple lines of code. Now in tomorrow's processor, you move it over to that one, no code changes, and you get tomorrow's benefit automatically. So this is the wisdom of using these kinds of libraries, is that you're putting that burden of the performance engineering on the library writers, and then you just reap the benefits. And that's the idea. So you're future-proofing your code. You're typically going to make it more readable. You'll see this in particular when we show you the NumPy examples, not this year, but next year. I'm hoping to get this on as one of the workshops. It can be jaw-dropping what you can get by using NumPy in the correct way. Many of you are going to roll your eyes and you just think, as I initially did, this is like an old dry hairball talking about NumPy, when we get there. And, I think we're just targeting March or something, but it's not. Many people think that they're using NumPy because they have NumPy arrays in their code, but then they're manipulating those NumPy arrays with a for loop, and that's highly inefficient. The intent of using NumPy is to use those built-in aggregation functions, those built-in ufuncs, those built-in broadcasting, fancy slicing, all these different tricks, which then use the MKL library that uses the C++ cache optimizations and so forth to really get you outsized speedups. And so it's just a plug for going down in the future. You're going to really want to take this NumPy class when we get there, because it will surprise you. And I'm going to show you some tricks that you can use NumPy even with pandas a NumPy where and select clause that you can actually use NumPy around a data frame and get speedups on your applies and so forth. So all these things tie back down to how do you take advantage of that instruction set architecture at the per core level. And that's what we're effectively doing right here with Scikit-Learn in this particular case. Okay, so anyway, let's analyze these results. I talked and talked. This is the performance result of the I think this is the fit function. So this is training. And you'll see that of the test harness functions that we did, and you are perfectly fine to plug in your own data set, that you want to test, synthesize it, read it, whatever you want to do, and try these algorithms out in your own sort of way. But this is a test harness that you can use to get a sanity check on your hardware, on your specifics, what is sped up. And you'll notice that here, on the fit function, the KNN classifier didn't speed up very much because the training function, the fit function on KNN, essentially just puts another log on the fire. It just adds data. There's not much to speed up. But these other algorithms speed up significantly on the fit function. And if we scroll down, we will see the speed up that we get on the predict function. This is the inference side, right? And so you get significant speed ups on some of these things. And then we'll combine the two and look at them all together, and you see this result that I showed you in the slides of the overall, the speedups you get for fit predict, right? This is kind of what you get. And so this is just a way of doing this to get the latest experience. I want to move on, if you guys are following, I want to move on to this unit right here on chapter 3. This is going to be important. This is on the strategy, the patching strategy. This notebook, 1_3, is it's not going to do anything. It doesn't run. It's not, the intent isn't to do anything in this notebook. It's really here as instructions to tell you what to do. You're going to launch a terminal, okay, and then you're going to do these kind of things. You're going to source the 2022 set var as variable, doing this. If it works for you, you can set the 2022.3. For me, I had to set the 2022.2. You're going to change directories. You're going to do a Jupyter notebook convert. And what we're going to do is there's a notebook in here that has a bunch of executable code. This is samples, SVC, or some samples, I forget what I called it. Let me just scroll across it. Samples SVM notebook, okay? And so there's a bunch of code here that we're going to want to speed up. So what we would like to do is experiment with different ways to speed this up by converting that notebook, first of all, to a Python code. You do that with Jupyter Notebook Convert, this to script. So I can convert a notebook to a Python file. Now I can run that Python file with the patch applied at the command line level, okay? And so when I run this code at this Python level, let's see, right here, just doing Python -m Scikit-Learn ex, it's going to run. Now internally, what's going to happen is that the first run of it will do the patch globally, and it'll take about 11 seconds. So it's going to inherit this goodness from the Scikit-Learn ex at the command line. But then within that code, we explicitly unpatch, and then that's going to take 1 to 2 minutes to run. And so what I want you to see, that even though you can patch globally, you can countermand that order by going into the notebook and explicitly unpatching a chunk of code. And in this way, you can explicitly control whatever performance that you want. You can make sure that you're only ever getting the best performance, right? By patching everything, kind of looking to you compare the two, and did some particular kernel, some particular loop slow down, some algorithms slow down, like the pathological case I found for train test split on a small data set. Well, if it does, unpatch that one, and you keep going. So it's a ratcheting function. You only keep the best. And so I want you to know about this strategy. Feel free to play with it. I just wanted to articulate what we're doing, and just know that this notebook 1_03 gives you the instructions for what to do, and it's all based on this patch core screen patching and so forth. Now with that, I want to show you, I'm going to, just so for the sake of time, I want to show you a couple of things. We're going to go to unit number 2 now. And this is, we're going to start going a little bit, still a little slow, but then it's going to pick up pace. Unit 1 is just patching the k-means using the CPU, on the CPU. No magic here. Find the instructions, insert your patch, and go. Okay, it's pretty much that simple. Now, this is this lexical thing I'm gonna ask you about. Okay. Here I've got a function, and so I'm going to do a lexical read of this code. This is if I printed it on a piece of paper and I read it from top to bottom. Okay. And so when I read this code, what I'm doing is I say, okay, yes, I'm defining a function. Okay, fine. He's asking me to import a patch here. Okay, I'll do the patch. Okay, I put the listener here. It will patch k-means. Okay, great. So I expect that I will get k-means to be patched, and it does. Okay, but if we do not put the patch here, what happens if we don't put the patch here? Where's the smart place? Because it's before the import, right? What if we instead put the patch after we did the import? So now we do the import, and now we do the patch. Well, then I'm arguing to you, you're not going to see any speed up, at least on this algorithm, right? Because the water's already under the bridge. You patched too late, right? But what if we put the patch right here? This is even later as we read it, but notice that the function definition for compute fit ended by indentation. It ended right here. So actually, if I put the patch here, this is a more global patch, right? I'm going to import before I dynamically call this function. You see the difference? So now this will patch, right? Because I'm doing the patch before I do this call, and this call is where I do the import. So I could either patch this in one of two places, but the third place right here in the middle, I would not have success patching. So you need to be thinking about your control flow when you do this. And this is just an example of how to do that. And so that's really the biggest caveat I wanted to call your attention to is just because you throw a patch, make sure you're putting it in someplace smart. Do it globally, do it at the front, at the beginning cell, do it at the front of some computation, whatever. You could actually put it at the lowest level within the function definition itself. But just be careful that when you play a computer and you pretend to be a thread and you follow the dynamic execution of that thread, defining the function is one thing. It's when you execute, right? So we're looking at the execution of that thread. And as you go through, did you patch before you did the import? If you did, you're fine, and patching will work. So I just wanted to call that to your attention, okay? Because there's little wrinkles here. Yes, patching is easy, but just give it a little bit of thought, right? This is just more of the same. I'm not going to belabor this thing. This is just using support vector machine, different data set, okay, get the patch, okay, fine. For sake of time, I want to save time to talk to you about a pairwise distance because I think it's an interesting algorithm. And so it's at first it feels like a dry hairball, honestly, pairwise distance, because you think, oh gosh, what am I trying to do? I'm trying to compute a distance matrix. Let me explain the algorithm first, okay? Pairwise distance, what you're going to do is here I've got 5 nodes, 5 vertices in a 2-dimensional coordinate system, okay? So I have X, Y data, but I'm going to just compute the distance from 1 to 2 and put that right here in this matrix. Then I'm going to compute the distance. Well, let's just see. The distance from 1 to itself is 0, right? Okay, well, we'll put that there. So this is the distance from 1 to 1 is 0. The distance from 1 to 2 is here, D1, 2. Distance from 1 to 3 is right here. Obviously, by symmetry, the distance from 1 to 2 is the same as 2 to 1. So, but while encoded as D21, it's the same numeric value as D12. So this is the distance from 2 to 1, the distance from 2 to 2, the distance from 2 to 3, and so on and so on. This is called a distance matrix. Now, there are different ways you can generate a distance matrix. What may leap to your mind is the Euclidean distance, and that's a valid choice for pairwise distance as a general rule. Some of you may think of the Manhattan distance, 3 blocks to the left and 5 blocks to the north. Okay, that's a valid metric for pairwise distance. Some of you may think of the cosine distance, and that's kind of from the dot product of 2 vectors, if you want to think of it that way, and finding the corresponding angle. Some of you may think of correlation distance, so how well are the 2 variables correlated? So there's different metrics that you can use for pairwise distance, okay? So just so you know, for purposes of the Intel extension for Scikit-Learn, we've only accelerated two flavors of this algorithm. The two flavors that we accelerated are the cosine distance and the correlation distance. Okay, we didn't accelerate the metric with the Euclidean nor the Manhattan distance. So then you think, well, big deal. Whoever uses the cosine distance for anything? Well, actually in AI, you use it a lot because you use it to compare documents. A lot of times you're looking at bag of words kind of a thing, and you would find the cosine distance between two documents or whatever is one way to do it. But I'm going to give you a different example. I'm going to show you an example for stocks. And so what I did here is I synthesized some stock data, 500 stocks, kind of like the S&P 500. I based it off of a couple of real stocks, Intel at some point in the past, and a couple of other tech companies, to find out what their betas and their basically the standard deviations and so forth, and created a random walk for 500 stocks. And I encoded that in a file. So we don't have to do the synthesis now. We just have the benefit of reading the data file. But I've got 500 stocks, and these stocks, we've got a data sample, about every 9 to 10 minutes for an entire year. Okay, so it's something like 12,000 or some odd rows of data, of time data, and then there's 500 columns, one for every stock. Okay, and it's synthesized, so I could actually use it. I don't have to get anybody's permission. Okay, so we'll read this stock portfolio, and I'll call it P for price. Okay, and so now what we'll do is we will just plot all of these stocks to kind of get a sense in one fell swoop if they feel stock-like. And okay, so let's plot it. That's ugly. Okay, yes, it is ugly. I'm plotting all 500 stocks, and I just wanted to show you that in general, overall, the overall trend, some stocks start somewhere plus or minus 50, maybe about $600. Some go down by maybe a factor of 2 or 3. Some go up by maybe a factor of 600 up to 24, a factor of 4, right? But gosh, that's ugly. But let's just pick 4 of them. Let's just look at 4 of those. I just wanted to argue that this could feel somewhat like an actual time series, right? 4 different time series right here. Could it be stock-like? Sure. Could this be data for Twitter feeds? Yeah, sure it could be. Could it be something for any kind of time series you want to think of? IT security, signals of some kind. Sure, it's just time series. And in this case, I said that it looks stockish to me, right? So, okay, great. So what I would like to do is I would like to do the following. I would like to see if those stocks fit. I'd like to draw a line with my finger or with some math tool, maybe principal components. I would like to draw some curve and say which of the stocks most closely follow that curve. Now, to do this, we're going to normalize the data because this data is spreading from minus 200 all the way up to like 2400 or something like that. So the first thing I do is I normalize the data. So that means by normalizing, what I'm meaning here is that it's got 0 mean and 1 standard deviation. Okay, so we'll normalize all the data to kind of get apples to apples comparisons here. And then that data we will use to create some shape patterns. Now, these shapes are based on sort of the same standard deviations and means that we were seeing. But imagine that I just took an index card and drew a curve and came up with a line, this blue line. And I just said, how many stocks follow this blue line? That's a shape curve. Or how many stocks follow this orange line? Or how many stocks follow the green line? Notice that the stocks that follow the blue line would be following a descending curve. I could just multiply that by -1 and find stocks that go up. Okay, this is my shape that I want to find. I could have drawn it. I could have computed it mathematically. Whatever I wanted to do, I come up with these kernel of shapes. Okay, so now what I'd like to do is well, let's just figure out what the data feels like. Let's look at the shapes data and we'll look at the price data. The shapes data has 12,000 rows and 10 columns because I've got 10 shapes, and 12,000 rows because it matches the number of 9-minute samples in a year. Okay, that's about 12,320. Same thing for the price. Okay, so I've got 500 stocks, 500 columns with 12,000 time entries in it. And then we can plot those or do whatever we want. Well, now what I'd like to do is to apply a pairwise distance to see if we can't solve the problem. I want to find all the stocks that follow this curve, this blue curve. You know that not all the stocks do follow that curve, right? Some of the stocks go up, some of the stocks go down. So which 4 most closely follow this kind of shape? Okay. And so to do that, what I'm going to do is I'm basically going to do the transpose of the data so that the time is now columns and the stocks are now rows. Okay. And so now you'll notice that for shape number 0 here, it has 1 row and 12,320 columns. And my prices shape is going to be, because now I've done the transpose of it, I've got 500 rows and 12,320 columns. And now all I do is I patch it so it's fast, but I'm going to do pairwise distance. I'm just going to say, put the transpose of the price data as my first array and put my shape 0 as my Y array. Now in this case, I'm going to multiply it by -1 because I don't want to be the downer that's looking at where the stocks are going down. I'm optimistic today. Let's see what stocks are going to go up or whatever, right? So I'm going to just compare shapes. And then since this data is normalized, I realize that when I plot this stuff, you'll see some hokey business down here about the scale offset and then the scale normalized. Really the smarter way to do it, and when I get a little bit of time later this afternoon, I'm going to tweak this slightly, because the smartest, all I'm trying to do is plot this data in something that looks like real stock units over here on the vertical column. But really, to compare shapes, what I really need to do is normalize this data, and plot the normalized stuff. And then I don't need to do these offsets and all this stuff. This is just to make the blue curve show up. Otherwise, it looks like a little flat line down here. It looks like a flat curve. And so this just shows, here are the 4 stocks that most closely match this curve, okay? And so this is just using the cosine distance. Now, again, I'm using the cosine distance because that's the thing that we accelerated in pairwise distances. And I'm here to argue that, hey, gosh, yeah, using the metrics for cosine isn't always a bad idea. Like there's actually places for this, right? And in AI, here's 2 cases. You could use it for time series. You could use it for documents, which is kind of the standard thing where you use it. Everybody jumps to the conclusion that you should be using Euclidean distance, and maybe that would work, but I didn't have an accelerated version of that. Okay. And so now what you can do is, now you can just go and play. This is find the 4 closest stocks that go down. Okay, this is the 4 closest for that. Let's look at, instead of we'll still use we'll use the correlation distance, okay, just to do something different. And we'll just find the stocks that most closely correlate to this cyclical stock pattern. That's stocks which start low, go high in the middle of the year, and go low again. Maybe if we inverted this curve, multiply it by -1 with the appropriate offsets, then this would be a typical sales cycle, revenue cycle for many retailers. Near Christmas, near the beginning and ends of the year, it's very high. In the summer, it goes low, and then it goes back high again. So you could find the stocks whose price performance most closely matches this thing. Now, I'm not here to argue that any of this stuff makes sense and that you're going to be able to do anything with this. There are people who swear by technical analysis for stock analysis, meaning that they have some shape called a cup and handle. And so, if I could draw this cup and handle pattern, could I find the stocks that most closely follow cup and handle? Sure. I'd have to do a little bit more work, because I'd probably want to use a convolution to shift that cup and handle left and right in time. We'd have to adjust the time base, because cups and handles could occur on the order of a month, a year, 2 years, so you'd have to do variations on this theme, but certainly we could find those stocks that match that pattern. Does that mean you're going to make money in the stock market? Not necessarily, and I would argue probably no. There's a book by Malkiel, an MIT professor, I think he's an economist, and he argues in his book, Random Walk Down Wall Street, that all this kind of technical analysis, all this stuff doesn't matter. At the end of the day, in the long term, stocks are going to go up on the order of 6% a year, irrespective of what you do, and there's no way to really game it. You can game it for a short time, and then everybody will start doing the game, and then the game disappears. So his argument is that all this stuff is silly. So I'm not here to pick a side, what you believe about technical analysis or any other thing. I'm just saying here is a technique by which you can use pairwise distance to find similar shapes, and maybe you hadn't thought of that before. So that's that one. So any questions so far? I know that was kind of a quick flyby of chapter 2. Any questions? Okay, so we'll just keep moving on. This last unit here, this is number 2. This is a telco customer churn example. This is a practicum for you. And by that, what I mean is, I'm not going to give you explicit advice of where to put the patch. You have to go figure it out yourself. So, but what you will be able to experiment with is, we're going to do some principal component analysis in here. We're going to do some k-means. We're going to do some DB scans. I think at the very end, I think I do some classification stuff in here to kind of predict churn. And so what is churn? The whole goal of this data set is to predict telco customer churn. Churn in a customer telco thing is this idea that you have a cell phone and you've been paying your cell phone bill either month to month or on some contract for some period of time. But then you get the idea that you can save money by moving to a different company. And so you switch your cell phone company. If you did that in the last 30 days, they call that churn. Okay. And they want to predict churn. They like to understand what causes churn. So what kinds of parameters? This is all tabular data. And if you look at this data, it's, all kinds of things like the phone service, how long have you been with them, the number of your dependents, your gender, whether you're a senior citizen, your marital status, technical support. Of all these things, what are the predictors? Okay, how many total evening minutes you ever used, or, of all these things, what, is the best predictor, or what's going to let you predict churn and to improve your revenue? Because if you can decrease churn, maybe maybe some targeted promotion, then maybe you can improve your revenue or your profits. And so this starts from the very beginning. This is the telco customer churn. It has certain object types, integers, floats. So all this stuff has to be feature engineered. It has to be turned into numbers. All these different utilities, that's kind of part of all this stuff. And so at the end of the day, though, what you want to do is to predict churn. And so, for example, marital status is not a number. It's yes or no. Gender is male, female. Like some of these things are text, right? And so you have to turn them into numbers. You have to, go through and do the one hot encoding, all this kind of stuff. So wherever you find examples of ways to accelerate this, your challenge is to do so. Standardizing the data. We're going to just do a correlation plot. We're talking about principal components. So we're going to create some principal components for all that data, and we're going to plot them on a scree plot. This just shows us how much of the principal components, if we use 19 principal components over here, we're predicting darn near 100%. We're probably 95% of the variance of the data. So we can compress all those 50 or 100 columns and knock that down to 19 columns, and we've still preserved the essence of our data. And then what do you lose if you only choose 10 components? Well, now I'm at 75% of the variance of the data. So you play with this, right? And then you begin to plot these things. So this is plotting principal components one after the other. This is a pairwise plot. So if you haven't seen a pairwise plot, this is Seaborn. A pairwise plot says let's plot principal component 0 against 3. So 0 is this dimension, and 3 is this dimension. And so we just plot them, and I'll plot them in 2 different ways. I'll plot them black to just say, well, there's a dot here, and then I'll plot the red ones when they happen to be a churn person. Okay, so they churned in the last 3 days, and this graph right here is principal component 0 is a horizontal axis right here. I don't know if you can see my cursor moving, and principal component 2 in the vertical. This is principal component 0 in the horizontal and 1 in the vertical. And the reason that principal component 0 versus 0, we just decided to plot a histogram. That's the default for pairwise, because it doesn't make sense. It would be a diagonal line. Plotting any random column against itself would be a straight line. So we just plot the histogram. And then we just rinse and repeat. This is principal component 1 against 3, 1 against 2. And so this is giving you a multi-dimensional view of the data with churn both on and off. So you can kind of see. Now the question is it just purely random? Are these pictures purely random? And I would say no. Randomness looks different than there's patterns going on here. There's at least a bimodal distribution right here that I can see right away, right? So there's two kinds of customers at least, okay? And then, the red dots line up on one side. If you're going to a pond to fish and you can fish in either this pond or this pond and you're fishing for red trout, well, I would probably go over to this pond and I would fish on this end of this lake, right? This end of the pond. So there's a pattern here, right? There's, here the trout are congregating down here, your churn trout are down here. So it's not purely random. So we have some kind of a hope that we can make heads or tails of this. And so now we can use clustering, we can use DB scan to find out more about the data. We can figure out how many clusters there are and how many outliers. DB scan gives you a value of -1 for values that it couldn't fit in your cluster definition based on the EPS and the number of membership requirements for a cluster. And so, we can play with these things. And this is the results of plotting DB scan and saying, well, it found 3 different colors, and then we can plot where the outliers are. And so, it thought that there were 2 different kinds of customers as well. And then there are people that don't fit. So you can do all this kind of stuff. Now you get the opportunity to go in and accelerate this stuff however you want. Do global, do surgical, whatever you want to do. See if you can get a speed up. And then we can keep going down. We'll do decision tree. And so the goal is, one of the only models that we don't accelerate with IntelliXM for Scikit-Learn is decision tree. Okay, just not enough benefit there. But decision tree is not, well, it's a fun one to kind of play with. It's easily explainable, for one thing. We didn't optimize it, but it's bigger brother, the random forest, which is generally going to be better for you in terms of overall predictability, not overfitting, a whole bunch of stuff, right? Random forests are almost as explainable as decision trees. We do accelerate that one. So I guess the goal that I would have for you here is in this exercise, see if you can't do this same module right here, but put in random forest instead, okay? And see if you can accelerate it, okay? You need to accelerate the principal components, the DB scans, do the whole thing, okay? That's your practicum. There are 2 other practicums in case you're bored with those. They're too easy. Then, now these are codes just like you would have found in somebody's blog on Medium or whatever. These happen to be my own, kind of ideas, but this is on image clustering. So we're going to do here's just another one of those pairwise distance plots where we're going to look at how dots cluster, and then hopefully we use DB scan or k-means to color the things that are close by, things that are clusterizable, things are in the same cluster, right? And so this data set is one that I generated myself just because I didn't want to get in trouble with a bunch of people. So what I did is I created a set of images from old vacations. And some of these are pelicans down by San Diego or LA. Some of these are in the coast. There's actually some dolphins in the seacoast here. Sometimes the sea looks green. Sometimes the sea looks blue. There's a bunch of colored lizards from out here in New Mexico. Now, it's the same colored lizard actually in all these photos. And this is an imbalanced data set. I intentionally made it imbalanced to kind of give it a little bit more of a challenge. And not only is it imbalanced, it's weighted a lot more heavily towards colored lizards. But the white balance between shots has been adjusted. So sometimes the colored lizard is dark and sometimes it's light. And if we're only using the RGB color space or even the HSA color space, hue, saturation, and value HSV, then can we do anything to cluster images, similar images together based on their color composition? And yeah, you can. And so the goal here that you do is, or my approach, you can take a different approach if you wish. My idea was to convert all these pixels into columns. Okay, so I've got 10,000 columns with pixel values in them, so that I have one picture per row. And then I do some principal components, and then I do some clustering, and then we just plot these things up, and we start to begin to say, well, if we categorize these things by the clusters that k-means finds, it does a pretty good job of finding all the darker lizards together. And then you can query this thing and see what happens if you change, in cluster rank, instead of 0, make it 1, make it 2, make it 3, and you'll see that different images are more closely related to each other than others. And there'll be some surprises in here, because the color space isn't necessarily the best way to do clustering, but that's okay. It does a fair job. And we'll do the same thing with k-means, and this is just the same pairwise plot stuff I was telling you about. This is how you can estimate using dbScan. To do dbScan, you do need to give it some parameters. The most important parameter is the EPS, which is kind of an epsilon that tells you, what's a distance. Like for this data set, you need to say a certain distance that you say, if it's within this distance, yeah, they're clustering. The other thing you give to dbScan is the number of members that it takes to become part of a cluster. Like if you find 3 or 4 points, is that enough? And they seem to become kind of somewhat close. Is that enough to call it a cluster? Or are you only looking for things that are gross level clusters, like things that have 10,000 elements in them each, right? So there's 2 parameters that you have to play with. Well, particularly EPS, you don't know what the right value to start with is. So I'm just articulating for you a couple of ways that you can figure out a good value of EPS to start with. And we're going to start with something that kind of plateaus over here. So we'll be using something like, negative 180 or something like that, right? And so it's just a way of finding clusters, finding the EPS. Here's another plot, and then we're going to find somewhere down here around 270 or so is like the minimum. So we'll try something like that to compute the number of clusters. In this case, I used EPS of 230, which is right, maybe somewhere in here. So then you plot it, and then you just see the results. And so now you can plot the images and see which images were close based on dbScan. Well, these all group together, right? So if you want to do these for stellar images or for whatever you want, where you have RGB color spaces for the different stars, the different intensities, like you could have a tabular data set that would do something very similar. And so this is just a way of these kinds of things. So I just wanted you to know what the practicum does. And then the last one I'll show you is number 4, which is kind of a toy little thing, but let me show you the video, because what I did is I synthesized 2 galaxies, and I rotated the galactic plane of one, and then I translated it so that they interacted. The planes, I can arbitrarily, I didn't put the code in here for you to synthesize the galaxies. I've got that code someplace else, but you can synthesize the number of arms. You can put in globular clusters in the various arms at random places. It's pancake shaped. Each one is kind of a disk or a spiral galaxy. Not all galaxies are that way. This only has maybe 100,000, 200,000 stars in it each, 170,000 stars in each one. Real galaxies probably have, 400 billion or, something like that, 100 billion. But let me just give you a sense of the shape. Matplotlib, which I'm using to plot this, does not do a very good job of showing the Z order where I could plot, where you could see the intersection. I just had real struggles with this. So what I attempted to do instead was to show you temporally and spatially, as I rotate these things around, that indeed they're kind of pancake shaped, that they do kind of intersect. And I do that by just turning the opacity down successively. And so as I turn the opacity down, any of the points that remain indicate that these are areas of higher density of stars, right? And so there's more stars, obviously, the way I engineered this thing, to be in the galactic centers than in the arms. And so I continue to turn them down. Eventually, what this animation will show, if you let it play long enough, if you don't get too bored, is that you will see a couple of red stars in here, 2 or 3 red stars. And what I did there is I used something like the pairwise distance or k-nearest neighbor, I forget which one I used, to find the 3 stars or 4 stars that are within 3 light years of each other, because of the interaction of the 2 galaxies. In other words, they would not be within 3 light years if just left alone in each of their own galaxies. They would be, they're not within 3 light years of anybody. But when you cause the 2 galaxies to interfere, they do. And so there's just a little bit of set theory we do to, kind of ferret out the ones that already are within 3 light years within a galaxy, each of the ones, and we go on. So this is just a practicum. What we're going to do is we're going to classify these galaxies. We're going to start with just 0.1% of the stars and see how well we can predict a galaxy based on just a random sampling of the red dots and a random sampling of the blue dots, to the tune of 0.1% for our training data, which is like crazy. Like, why would you do that? It's way too low, right? And then we increase it to like 1% and 2 and 5 and 10 and 20 and up to 80, right? So we see how much classification it takes to do a fairly good job of classifying these stars and which galaxy do they belong in. And I gave names to the galaxies too. One of the galaxies, let me just see here, I called it Zeno galaxy. Zeno is kind of the galaxy that Superman's Krypton, planet Krypton, is from, according to Superman lore. So I called one of the galaxies Zeno. I called the other galaxy GFFA. Any ideas what GFFA is? It's galaxy far, far away. Maybe if you are a Star Wars fan, you'll remember the words, but galaxy far, far away. So these are 2 fictitious galaxies. And I just cause them to interact, and then we will just see how we can classify them. So the goal here is I'm going to classify 2 things in kind of a pipeline fashion. So I put them in a dictionary, K nearest neighbor and random forest. And then here are the training subsets that we're going to use: 0.1%, 1%, 3%, 5, up to 80%. And then we're just going to put this in a loop and do some training. And then we just attempt to find out what algorithm is the best, and what obviously the more training data that I use, the better the classification is. But do we see a spot where I don't have to train on 80% of the data? Is there some other place? And so you will find that. And then I'm just going to articulate to you that we're going to get ready for next month we're going to set the stage for being able to do GPU experiments. And to do that, I do something called a we're going to write this entire cell using a cell magic right here. We're going to write this entire cell to a file called practicum analyze galaxy batch.py. So this Jupyter Notebook cell gets turned into a Python file. Okay, that Python file, now this is just the way we QSub it here on DevCloud. That Python file, we've got a Q bash shell script that basically submits this in a QSub fashion to another node on the GitHub, okay, or on the DevCloud, I mean. And so what we do is I've got a shell script that we actually run on that node, and that shell script is run model compare. Well, let's take a look at run model compare. All it does, this is like boilerplate up above, it's just echoes. It's not doing really anything. It sources the environment. But all it does really is call Python against this file that we just wrote. And so that's all it is. Now, we're going to be doing this right and left when we do the GPU stuff next month. So I wanted to kind of introduce it to you. But this is, now we're just doing a Q submission against some node, a Xeon node, and then we're getting some results. And so we told it, or in this case, we actually even requested a GPU node as well, not that we're using it yet. But what we're getting is both the time, what the classifier that we're testing is. So here's K nearest neighbor. Here's our rock score. So imagine that at just sampling 0.1% of the stars, probably because they are pathologically created to be in a galactic plane. Even at 0.1% of the stars, though, it's got an 87% rock score, which is huge, right? And then as we increase the percentage of training that we do, so we're training on only 1% of the stars, we're at 94%. And then we can continue on. And the percentages don't really improve that much, even when we get up to 80%. But you can kind of choose what your best classifier is. So this is a way that you could use, again, if you wanted to test your own stuff out. It doesn't have to be this data set, but how do you patch that? What do you do to patch this more complicated code that has these, kind of this pipeline in it? And how would you do that? And where do you put the patch? And so that's the practicum. So with that, that's kind of the lab, and hopefully you guys have been able to play and so forth.